Hello everyone. So I'm going to be solving this problem because it seems like there are some students who would like to review this material again. So what do you do when you encounter a question where you have a binary format of assembly instructions given to you, and how are you going to convert them into assembly code, and then after that, how are you going to solve a problem? So as you can see here on the left, we have the addresses, memory addresses of where these instructions are and where they are going to be executed from. So for you to execute this instruction, you are going to need your program counter to be set to x30f6. Okay, so how do you start? The first thing that you are going to do is that you are going to first identify the operation codes. On LC-3, since the operation codes are the first 4 bits of the instruction, you are going to first write what these instructions are. And then after you find out what these instructions are from the instruction set architecture that you must have in your hand, again, in that instruction set architecture, you are going to look up what this instruction is and how it is structured. For example, for LEA instruction, you are going to see that the 3 next bits after the operation codes will give you the destination register. And then the rest of the information is program counter offset. I would like to remind you that all of these items, all of these intermediate immediate numbers are in 2's complement. So this number here corresponds to -3 in decimal. So, and then the next thing that you are going to look at is the next line, obviously. So the next 3 bits after the operation code in an add instruction is going to be your destination register, where you are going to write the result of the operation. And then the next 3 bits, here is going to be the first operand of the operation. When you see 1 here in the bit number 5, you are going to understand that this add instruction based on the instruction set architecture is an immediate instruction. So these 5 bits remaining in the last is going to give you an integer. In this case, this number corresponds to 14. And then in the next line, you are going to take a look at store. When you look at the instruction set architecture, you are going to see that the next 3 bits is going to give you the destination register again, the source register in this case, where the data that is stored and produced by the CPU, in this case, it is R2, is going to be copied over into the memory. But these numbers here is now representing the program counter offset for store. So you are going to take the program counter, you are going to add this number into the program counter and find the memory address that the value in this register to be written. And then in the next line, same thing as this second line here. This number, these 3 bits represent the registers that the operation result will be written into. The next 3 bits is the first operand. 1 tells us that this is an immediate operation. So we are going to be adding this number, whatever that is in this number, with 0. And then this time it's an add, not an and, sorry. So we are going to be performing a bitwise operation here with R2 here. So we are writing, when we do the bitwise operation, and with 0, the result is always 0. So we are writing 0 to R2 here. And then the next line, add, again, this is an immediate operation. We are writing into R2, reading R2's result and adding 5 here with this immediate number. Here we look at the offset, store offset. So what we are doing here is that we are going to be writing the contents of R2 to an address here that is, we take as a base from R1. R1 is a memory address in this case. And then the immediate number, we are adding R1 plus this immediate number and finding out our new memory address that we are going to be writing the contents of R2 here. And then this LDI is, again, the first 3 numbers after the operation code is going to give us what register that we are going to write into when we read from the memory. And the next numbers is, again, program counter offset. But since this is an LDI operation, how it works is different from the regular load instruction. We are going to talk about that just in a little bit. So, okay. In the next step, we are now going to start how this operation will work out. So first, LEA instruction. So like I said, this is -3. LEA takes the program counter, adds the offset into the program counter, and writes that memory address into a given register. In this case, we are writing into R1. Since the program counter here is X30F7, Y7, because whenever we started performing this operation, this instruction, we have already incremented the program counter. So every time we start executing an instruction, the first phase, fetch, is going to increment the program counter. So LEA is going to add this -3 into program counter X0F7. And the result of that is X30F4. We are going to write X30F4 into R1. In the next instruction, we are going to add R1, because here is the register, to 14, this immediate number, and write into R2. And then since we had X30F4 in R1, when we add it with 14, it's going to be 3102. You can make this computation with hexadecimal, or you can turn both of these numbers into binary and add with binary, whichever you are comfortable with. But make sure that you can do those operations as quickly as possible. And then in the next line, we are storing the contents of R2 into program counter plus -5. So that's going to be an address, because the store operation is going to add the program counter with this immediate number, and it's the memory address that we are going to be writing our information into. And where does this information come from? This R2, 0, 1, 0. And then we perform AND operation with the contents of R2. Why? Because in this case, we are trying to reinitialize R2, right? 0 into R2 in this line. And then we are adding 5 into R2. This is an immediate number, if you remember. So R2 is now 5. In the next line, we have a store information, but this str is different from st. When we have str, that means base plus offset, not program counter plus offset. So just like normal, for is store operations. This 0, 1, 0 is going to be where we are going to be copying our content from. And then we are going to be writing into a memory address where here is the register, the base register that we are going to have our base address from, and we are going to be adding the offset into that address. In this case, that register is R1, and I'm adding 14 into R1. So what did we have in R1? If you remember, we populated R1 here. In our first line. We didn't change R1 at all since then. So the address, when we add 14 into 30F4, it's going to turn into 3102. Since we had value 5 in R2, we are going to be writing 5 into 3102. And then we are going to execute our last operation, LDI. Well, in this case, LDI operation, we are going to be loading information into our registers. In this case, the register that we are going to be writing into is 011, which is our register 3. So we are going to do a program counter offset here. The difference between load and load indirect LDI is that in LDI, we are looking at a pointer in the memory. So what we are going to do here is that we are going to take the program counter, add -9 to the program counter, which the program counter is x30 f d, because when we started this instruction, it was 30fc, and when we started this instruction, it got incremented by 1. So the program counter is 30fd. When we add -9 into this one, since d is 13 in hexadecimal, -9 makes this d turn this d into 4. So the memory address that we are going to look at is x30f4. Well, memory x30f4, if you remember, it contained an address here that we have written into, and that memory address is x3102. X3102. So we are going to now go to memory address x3102, which was what we wrote into in the previous line with 5. So that means we are going to be bringing 5 from memory address 3102 and write it into R3. So the only time that we write into R1 was the first line. That's why R1 is going to be x30f4. The last time that we wrote into R2 was this line, so that's why R2 is going to be 5. And the last time that we have written into R3 was this line, so we brought 5 from the memory and wrote it into R3. That's why R3 is 5.